My power went out.
Oh no. Yeah. Oh.
I was like,
Did they just turn it off? Like what happened? Or was it like some power line went out or?
yeah, I think it's because of power line. Like the entire neighborhood I was in, everyone's power.
Yikes. In California, they just turn it off to avoid fires, but here maybe not.
Why they call it bomb cycling?
Good question.
That's kind of scary.
Yeah, it's kind of scary. Okay, let's get started. So today we are going to finish off inverse RL. We'll start doing multitask RL, and next Monday we'll do offline RL, and that'll be our last lecture. And then Simon will lecture on Wednesday. I think we're done. So our structure of our class today is going to be, we'll just recap max margin and max end IRL. We went through a lot of algebra last time. Let's just recap it quickly. Then we talk a little bit about how we can make max end IRL practical. So how do we do it with deep networks and gradient-based optimization and like easy updates? Then we talk about how we can actually recast IRL as a GAN and use a lot of the machinery from a GAN. And then we switch over to multitask and meta reinforcement. Yeah. Okay, so let's get started. So to recap, the problem statement of IRL was that we know everything except for the reward. You're given you don't know the reward, but you're given expert traces, as opposed to RL, where you're given the reward, but you don't know the expert traces. Right? And so the problem statement needs you to find a reward that best explains the demonstrator behavior as noisily optimal, right? And so we collected data, we found a reward function. That reward function can then be used to find a policy and a new scenario, right? That's inverse RL. So we covered a couple of ways to solve this problem. The first was max margin. And the idea of max margin was that we wanted to say the value function for the optimal data is better than the value function for every other policy, right? And we said that is inherently ambiguous. And so we introduced this like max margin formulation. So we want to say it's better than every other policy by a margin. We want to maximize the margin. And so that is the max margin formulation. The max margin paper just adds some sauce on top of this basic max margin SVM formulation. Just allows for some policies to be suboptimal, some expert data to be suboptimal, and it allows for some structure in your problem. So that's the idea behind max margin. It's just saying that expert data is better than every other thing by a margin. Maximizing margin. And then we went through, okay, so this gives us an algorithm which says you get a reward function. You then solve this constraint optimization problem. Constraint optimization you can solve with a convex solver. It's a linear problem, and then you repeat. Right? And so the challenge with this objective is that you have to solve this constraint optimization problem. Hard to do with neural nets, hard to do with gradient descent. And so what we did instead was we tried to derive it from the perspective of maximum entropy. So we said we want to find a probability distribution P of trajectories, which matches the expert. But because that's ambiguous, you want to find the highest entropy distribution of trajectories. So you want to maximize the entropy while matching features to the expert, right? And so the first term is maximizing entropy. Second term is feature matching. And then the last one is just like a valid probability distribution. And so that's our basic objective for max entire.
Could you just briefly explain like the intuition of maximizing entropy as like your data?
Yeah. Yeah, so it's max. If it is just maximizing entropy, you just get the uniform distribution. But what's happening here is you're maximizing entropy while ensuring that the feature expectations match the expert. And so you're saying that essentially what you're saying is things that the expert thinks are good, weight highly, and everything else be as uniform as possible. So like try to avoid bias towards anything else. So you're not actually going to get the uniform distribution because of those constraints. Good question. Okay, so we started with this objective, and we did a bunch of convex optimization-y things. Have a question?
Yeah. Why is that a good thing to like not have bias? Is it something like there's many explanations for what just happened. And so where you have expert applications, you want to be the same as expert,
Yeah.
or where you don't, you want to be somehow.
Yeah. It's like placing a uniform prior on all of their behavior. So it's like on all of the behavior, you don't know what happens. And so you're like de-risking. It's kind of like robust optimization, you also de-risk, right? Similarly. But it's a choice of model. You could choose a different model.
Hmm.
So there's a field of Bayesian IRL where you choose different priors besides this one. But this is a choice of the uniform prior. Okay. So this is our Maxent IRL formulation. How did we solve it? We set up the Lagrangian. The Lagrangian had these two Lagrange multipliers, W and lambda. Then we swapped the max and the min, and then we solved for P and lambda, and then for W, right? And so we just went through this algebra. We just took the gradient of this thing, set it to 0, solve for P. Then took the remaining expression, took the gradient with respect to lambda, set it to 0, solve for lambda, substituted in to get an equation for W, right? And W's are like reward weights. And so what the resulting objective looked like was something like this, where your objective is min log z minus W transpose mu pi star, where z is the integral W transpose mu tau, where mu tau is essentially just the sum of features, sum of discounted features along a trajectory. So this is going to be mu tau. You take a trajectory, you take the features, you sum it up along that trajectory, that's mu tau. And so you can see that this objective essentially simplifies to something like this, which says we want to maximize the log likelihood of this probability distribution. Let's call it dw tau, where it's saying that like the likelihood of a trajectory is equal to the exponential W transpose mu tau by integral x W transpose mu tau. So it's what you call the softmax, right? But it's basically saying things that have higher rewards. So if you think of rewards as bigger, then W transpose mu tau is your return along a trajectory. So trajectories that have higher sum of rewards are weighted higher. Trajectories that have lower sum of rewards are weighted lower, right? And so when we work through this algebra, basically you get back to maximum likelihood learning, the same as supervised learning kind of, but your probability distribution that you're doing maximum likelihood on is this softmax distribution, right? And so it's saying that like whenever you have anything max set, remember that it comes out to be some sort of a softmax, which says that your likelihood is proportional to your exponential utility or exponential reward, right? So, and if you're interested in like Bayesian models of cognition, it's often called Boltzmann rationality, like the same idea. But it's basically saying it's like a soft notion of optimality. Right? So it's like things that are not the highest reward don't have a weight of 0. They just have a weight proportional to their reward. And you can change how sharp that function is by scaling the reward. Okay, so when you kind of like simplify the whole objective, you get something that looks like this. You're trying to find the W, which maximizes this likelihood, right? So you can kind of think of this as dw of tau, right? This like internal thing. And you're trying to say for trajectory sample from the expert, I want to maximize the log likelihood of bw of tau. Okay? So I want to increase the likelihood of things from the demonstrations under this distribution, which is essentially going to weight the good things good and everything else equally because of the maximum entropy, right? So, Maxent IRL starts from this thing and just simplifies to a maximum likelihood problem under the softmax distribution. So that is MLE under softmax. Okay. Does that make sense? So intuitively just saying like, try to find a W which weights the like good trajectories high and the bad trajectories not as high. So what's the problem with solving this objective? Why is it hard? Log integral is horrible. So we need to avoid log integrals. And so the challenge with this is that you have a log integral in the denominator. It's hard to estimate it. But through the magic of more algebra, we arrived at this solution, which is a bit better, right? So we took the gradient of that objective, and you get something that looks like this. And intuitively, I'm not going to rework it out, but you can kind of think of this as like a difference of two terms. One of them, which is going expert of log x w transpose mu, and the other one is integral x w transpose mu. And then you try to take the gradient of them, or sorry, log integral. You take the gradient of them, and you come out with this expression. This expression intuitively makes sense. It says that push up all the stuff in the data and push down all the stuff that is drawn from the soft optimal distribution. And so the soft optimal distribution is this distribution. It's a distribution where your sampling trajectory is proportional to how, like, to their W transpose mu, right? So under your, like, the second distribution is saying that under your current W, you're going to sample trajectories proportional to X W transpose mu, push those down, right? The nice thing is that this is the solution to maximum entropy RL. So like soft actor critic will give you this answer, right? And so all you have to do is you have to like, to do max and IRL in practice, you have to start by taking your current policy or taking your current reward function, solving pi to soft optimality, right? So run SAC or soft Q learning or like some maximum entropy RL procedure. What you'll get is some distribution of trajectories. You'll get some trajectories that come from your pi star. And soft maximum entropy RL says that this pi star is the same as this distribution. And so you sample from this pi star, and then you take an update step on W, right? And then you solve for pi star again. Okay, so inside inverse RL, you have a loop of RL. To run max and RL to convergence, once you have a convergence, you take a step on W, and you solve it to convergence again, and W convergence again. And so the RL part is like hidden inside here. Yeah. Okay. Any question? Yes.
Sorry, what specifically is fine? The fee? What is fee? Like, we set the reward equal to.
Oh, fee is the features. So it's saying that your rewards are linear in some features. So like everything we derived so far has relied on linearity. But the next thing we're going to do is remove the requirement for linearity. So essentially, the only reason we have fee is because rewards may not be linear in states, but they're linear in features of state. So phi can be a nonlinear function of S and A, but we know that reward is linear.
So is phi like a neural net that's learned somewhere?
So what folks would do when they were doing max IRL is you would hand design features. They'd say like, there's a distance of the arm from this thing, and the like how fast you're going and your velocity, and there's like some number of features of your states in action. And then you're going to say that your reward is like some combination of those features, right? So that's like hand designed, and next we'll try to do it not hand. Okay, does it make sense to everyone? It's IRL has RL in between. You basically push up data, push down everything else, and you just keep updating the push down distribution.
So you said any for RL that has a max entropy,
That's right.
or how do you know exactly that SAC will represent that P?
If you like work out the Bellman equation for maximum entropy RL, so like if you go back to your Bellman equation and add an entropy term, and then you work out exactly what the Bellman equation will be, you'll see that the optimal of the Bellman equation is that. I refer you to like in my CSE 542 class, I had like 3 lectures on controllers inference. They like go over it in like excruciating detail. So like take it. You could also read the soft Q learning paper. It also talks about it. But here's some intuition, Thomas, that might help, which is like RL tries to find the trajectories that have maximum reward. This is kind of like a soft max reward. So it's trying to like adding entropy generally like softens things. And so it's saying that like imagine this thing, if you scale your reward, if you scale your W to be really big, then it becomes the max. Right? So it's like basically if you have a soft max, like a soft max is something like this. And imagine that you were like decreasing the temperature on your softmax, which means that you're making your softmax sharper and sharper and sharper. And eventually it becomes a Dirac delta at the max, at which case it becomes regular RL. And all that entropy does is it kind of softens it. So that's kind of intuition. But for a formal definition, look at this control resistance metric. Okay, so that's max and IRL. So we put it together, we propose a reward function. Then we like optimize max and RL against that reward function. Then we do this push up, push down thing, right? So we push up things that are in your expert and push down things that are coming from your expert RL policy. So you push up things that are in your like human provided expert, and you're pushing down things that are in your current optimal policy. Right? So this goes up, this goes down, and then you repeat. Yeah. So that's max and IRL. Okay, so would I ever do this in practice? What makes it hard? Like why is this not what Google Maps uses?
Running RL.
Running RL in the loop is hard. The other point is that rewards are not linear, and how do you choose these, right? And so let's get to this. The next thing we want to figure out is how to make this max and IRL procedure practical. So how do we get rid of this like complete RL in the loop thing? And then how do we do it with deep neural nets and like richer function approximators without requiring this fee to be hand designed, right? Okay. So people did end up using it, right? So this is some stuff from Oxford, I think, where they were like navigating around their campus or the city, forget. Unless their campus is that big, that seems kind of odd. But it's probably around the city. And then this is some cool stuff from Google Maps where they on the top is shown how much improvement they see in Google Maps performance in different cities. And you can see that it's like fairly significant, especially in Vegas and Kyoto. But yeah, it's like essentially like the thing on the bottom shows that like they find paths that go through like open gates and like avoid really narrow streets because they look at the preferences that people have for driving through those. And so it does seem to work in practice. So what kind of changes did they make between max and IRL in this? The first change that they made is let's kind of relax these two assumptions. Let's relax the assumption of linearity, and let's just relax the assumption of known dynamics. And so the logic is really simple. It's saying that let's instead of writing our reward as W transpose T, let's write a reward as some neural net which takes in S and A. Yeah. And you can like kind of reinterpret max and IRL as pushing up the reward on expert demonstrations and pushing down the reward on demonstrations from your soft optimal policies, right? But that doesn't have to be linear. And so the thought is that if I like represent my like here it was linear, right? My reward is W transpose P. But you can just represent this by some nonlinear function R theta, right? And so you can say that the same objective that you have can be basically maximizing the sum of rewards for the expert and minimizing the sum of rewards for the trajectory from the soft optimal policy. So you're going to do exactly the same thing, but rather than taking the gradients of a linear thing, you're going to take the gradients of a nonlinear thing. Right? So you're going to represent R theta by a neural net, right? And then you're just going to use auto differentiation. So the same thing that you did earlier, you're going to have basically a gradient. Sorry. You're going to have something which is like the gradient, or you're going to have expectation of trajectories drawn from the expert of the gradient of R theta top going up. So increase the reward on the expert, and you're going to like take trajectories drawn from the soft optimal policy and decrease the reward on trajectories from the soft optimal policy. Right? And so all you're going to do is just like compute these gradients with autodiff, PyTorch, but you can apply exactly the same objective. Same objective pushes up rewards on expert data, pushes down rewards on trajectories drawn from the soft optimal policy. Yeah. And so the only change is that you're going to change your you're going to change your reward class to be nonlinear. You're just going to use auto diff to compute your, like when it's linear, you don't use auto diff, like you know what it is, right? Like for instance, if it's linear here, you can just sum up the features. There's no gradients needed. Whereas if it's a nonlinear function, you have to use auto differentiation, increase the rewards on expert, decrease the rewards on trajectories from the soft optimal. Right? And so you would just construct a surrogate objective like this, right? Something that pushes up some stuff, pushes down some stuff. Use auto diff to update R theta. That's it. Yeah.
So what part of the prior gradient that we derived relied on linearity?
Nothing.
Uh,
It's like well, that's not true. I guess if we look at the derivation that we actually did to go from there to there, we use like the fact that it's linear here, right? But I think when you derive this thing from the perspective of like a softmax distribution, you can think of this as just like your trajectory distribution is proportional to the exponential reward. And so linearity doesn't matter. Right? So you can just rederive. Basically, once you get to this thing, you rewrite it as x arc theta. You don't care about linearity. You can just redirect the gradient of this thing with respect to theta. So that works out. Like you can think of this one easier as just pushing up some features and pushing down some features, right? Pushing up some feature weights, pushing down some feature weights. With r theta being nonlinear, it's a little harder to make the same analogy. But yeah, you can use the same procedure. The same procedure being just like take grad theta r, push it up on expert, take grad theta r, push it down on things from the soft optimal policy. That's it. Okay, so does that make sense? So all we did, we worked out max and IRL, and we said that actually, as Thomas was just saying, like it doesn't actually depend on linearity at this point. So you can take the gradient with respect to a nonlinear function, and you can just work out nonlinear max and IRL. It's pretty much the same. Yeah. The only difference is that you have to do RL now with a nonlinear reward, but that's fine, right? Like RL with a linear reward is often easier, but when you're using SAC or soft Q learning, it doesn't matter. Just run RL. Okay, so that is the first problem. The second problem is that we're doing RL all the way inside the inner loop, right? So we need to get samples from this. Sorry, here we go. We have to get samples from this like EW star thing, which means I have to run RL all the way to convergence, right? Which is kind of a pain in the ass. Every time I take an update on a single on W, I have to like run RL all the way to convergence. So I want to like avoid doing that. How might I avoid doing that? Given all that we've learned in this class, are there tricks we can do to avoid doing that? The problem is my second term has to sample from the soft optimal policy, but I don't want to solve max and RL. So are there other things that I can do?
I think it's not a good idea, but like if you were to just drop that term and just maximize the like likelihood of the expert characters.
Yeah.
So like it's arrived.
The tricky part is that then there's nothing that prevents everything else from also going high, right? And so what you really want is like, if this is your optimal behavior, you want this thing to go up and you want it to be higher than everything else. Like if you don't push other things down, then these ones will also go up potentially, right? And so you can't fully drop it. But maybe what we want to think about is like, how can we approximate that second term? So second term is basically something like this. Now, the problem is I don't want to sample from this guy. Yeah.
You do something similar to replay buffer, where maybe replay buffer is not the right word, but maybe you want to train the SAC somewhat before you start saying.
Exactly. You want to train it somewhat. So I want to take like one step on SAC or take a little bit, a partial optimization on SAC. But the problem then is that I'm not actually sampling from this guy, right? Let's say my SAC was like some pi, and I started with some pi and I stepped to pi prime, right? But unless this is pi star, that's not the same as this guy.
Like, could you train SAC on a subset of your reward to?
But then you'll still incur bias, right? Because so maybe let's think about it this way. We want an expectation according to some distribution P. But I don't have P, because P is a pair of yes. But instead I have Q. So how would if I have samples from Q, which is my little bit of SAC, then how can I evaluate this expectation using Q? Important sampling, right? So what important sampling says, I guess, is that if you take this expectation, you can approximate it with expectation Q of P over Q times F, right? So let's say we didn't want to run policy optimization till convergence. What we could do is we could run it a little bit, and then we have to correct for the fact that it's not actually the right distribution by important sampling.
I thought we don't have P, how do we evaluate P?
It's a good question. Let's look at that in a little more detail right here. Yeah, so we don't know P. That's Rico's point is we don't know P, right? So the logic is let's improve the policy a little bit, and we want to deal with this issue that we don't know P, right? The problem is that if we just improve the policy a little bit and use that to push things down, that's from the wrong distribution. And so we want to do an importance weighted correction like we just talked about, right? So importance sampling is our friend. And so we want to replace this with a different distribution. So we're going to replace it with some distribution Q. Okay. Rico's point was we don't know P, right? But if we think about what P and Q are, let's say we had a current policy pi, right? The likelihood of a trajectory under my current policy pi is, if you remember, it's like the likelihood of your initial state times the likelihood of A0 given S0 times the likelihood of S1 given S0, A0, and so on. Right? You just multiply the initial state times the policy times the transition dynamics, and you just do this over a whole trajectory. So that is what Q is. It is basically initial state times your current policy times your transition dynamics times your current policy times your transition dynamics and so on, right? Now, Rico's point was we don't know PW, right? We don't know PW tau. But what maxent RL tells us, which we didn't have enough time to cover in full detail, but basically tells us that if I'm trying to get the optimal distribution with respect to some maxent optimal distribution with respect to some reward, you can show that this top distribution is proportional to P of S naught times P of S1 given S naught A naught times the exponentiated reward of S naught A naught times P of S2 given S1 A1 times the exponentiated reward of S1 A1. So we know that PW tau is the optimum maxent policy, and you know that I'm going to state this without proof, but you know that the optimal maxent policy, it's the likelihood of that trajectory is proportional to the initial state distribution times the dynamics times the exponentiated reward times the dynamics times the exponentiated reward. And so you can show that the likelihood of a trajectory in the numerator is just going to be a product of the initial state and the dynamics times the exponentiated rewards multiplied together. And the bottom is just going to be the product of the policy likelihoods, right? And so intuitively, you can think of it this way, is we know from our soft optimal policy that the likelihood of a trajectory is proportional to the exponentiated sum of rewards, right? That is the whole premise of this distribution, right? So we know that PW tau is proportional to the exponentiated sum of rewards. And so essentially what this simplifies to is the numerator becomes the exponentiated sum of rewards. The denominator becomes the product of the policy likelihoods, right? And so this is something you know, this is something you know, and so you can evaluate your importance weight. And so let's just recap what we did. We had this thing, pain in the ass to do the whole optimization. So we're instead going to take a little step. So you can think of Q as a little step on your current policy. not an optimal policy. Now you take a little step and the numerator is proportional to the exponential to sum of forwards. The denominator is proportional to the product of the policy likelihoods. And all of the dynamics cancel because you're in the same environment. So all the dynamics, everything cancels. The only thing that remains in the numerator is the exponential to sum of forwards. The denominator is policy likelihoods. And so these are things we know. These are things we know. And so we're golden, right? Why is this still, it's not that easy to solve this still. Why is it not easy to solve? If you remember, when we derived TRPO, there was this like problem with importance weights, right?
Products.
Yeah, you have a product of a bunch of terms, right? So here you have a product of a bunch of terms across the whole trajectory. That's going to be really high variance. And so in practice, when you do this, the nice thing about this procedure is that it starts to look something like this, right? So rather than doing full policy optimization, you take a step on your policy, and then you take a step on your reward function, and then a step on your policy, and a step on your reward function. And the main thing that changes is that this importance weight is going to keep changing, right? The tricky part is that these importance weights kind of blow up. So that's what makes this a little hard to do in practice. So what we fixed though is we said this used to be linear. We've now made it a neural network, right? And this thing used to be full RL. Now we just do partial RL. And we fix it with these importance weights, but there's some amount of blow up in the importance weights. So in practice, what you often do is you like flip the importance weights from blowing up and it does okay. So it's kind of like Jacob's suggestion of like dropping parts of the second term. Okay, does that make sense overall? So we try to make inverse RL more practical. We said that's going to be a neural network. This is going to be partial optimization. We're going to fix it with importance weights. And it kind of works. So this is some stuff where they demonstrated like putting plates into a dish rack. Paper called Guided Cost Learning. And they showed that they can generalize something more plates, hand coded costs. Using this like correction seems to like get precision and relatively efficient optimization. Okay. So that makes IRL a little more practical, right? So the resulting algorithm we have is like something we can run a gradient descent on. Right? There's nothing is not gradient descentable. This is a neural net. You're doing one step of RL, and you can use whatever RL algorithm you want. You're doing one step of gradient descent on the reward, and then you're repeating. Right? So it's all, this is something you will implement tomorrow. But that's it.
So when you're figuring out the reward, like one way to use the reward is like in NVRL, right?
Yeah.
One of the questions that I've had is, I guess like you in a previous slide you had this statement saying that you're assuming that the dynamics are in the mode. What happens if like in the real world I have some dynamics and I can never actually have those dynamics? How do we account for that?
So either you have to assume samples from the true dynamics, or you have to assume that something is known about the true dynamics, right? Otherwise you're optimizing a surrogate model with no knowledge of the
Right.
true
So
dynamics.
if I have samples from true dynamics, then
Yeah, so then you just run RL with those samples, right? So like we learned, for instance, we do off policy RL. You do off policy RL with the changed report. Right? So you can run off policy RL on whatever data you want. You collect some data in the real world. You don't need to have known dynamics. The reason known dynamics is really useful is because with known dynamics, you can solve this step blazing fast. Like imagine you have tabular dynamics, there's a big table, you just have to solve some system of linear equations to get your answer, right? Whereas if you can only get samples from it, you have to run RL, but you can run one step of off policy RL with that reward. And so the tricky part is your reward is changing, right? So every iteration your reward is changing. Okay. Cool. And the result of this kind of procedure is you come out with a reward and you should come out with an optimal policy. And so most of these procedures will come out with rewards and optimal policies. In a new setting, you can have the same reward and you might be able to fine tune your policy. So if the dynamics change, your policy may not work, but your reward. And so there's a bunch of papers on adversarial IRL, which try to like talk about how these rewards transfer. Okay, and that's why we want to do IRL and not just BC. Good. So that is making Maxent IRL practical. How are we doing that? The last bit I want to cover with IRL is like a really interesting connection to GANs. How many folks know what GANs are? More or less? Okay. So just to kind of like make the connection intuitive, you can kind of think of this procedure of Maxent IRL, right? As you're doing two different things. You're like taking a step on your reward. You can kind of think of your reward as a discriminator, and you're taking a step on your policy, which is kind of like your generator. And we're going to show why that makes sense in a sec. But try to think of it as a game where your rewards are discriminators and your policies are your generators. Right? And so we'll try to make that. I will try to make that a little more formal, right? But GANs generally are a class of methods for generative modeling. So in generative modeling, you're given a bunch of samples and you're trying to generate new samples from that distribution. So you're given a data set of samples, let's say you're given a data set of faces. You want to generate new faces from that distribution. And it's typically hard to do because it's hard to parameterize expressive families of probability distribution. That's why you have diffusion models, that's why you have GANs, that's why you have normalizing flows, that's why you have flow matching, like all of them are solving the generative modeling problem. And the idea behind a GAN is that it's hard to get tractable log likelihoods, but you can cast this as a two-player game. So you have a two-player game, you have a generator and a discriminator. The generator is trying to confuse the discriminator, and the discriminator is trying to tell the difference between samples generated by the generator and real data, right? And so essentially, the generator is going to generate samples. The discriminator is going to try and figure out if those samples came from the data set or they came from the generator. So that's the intuition. And the point is that at convergence, your generator is going to completely confuse the discriminator, right? And so your trajectory or your images are indistinguishable as a distribution from real images. And the argument is that if you can do that, then you've like figured out the distribution of real data. Okay, so the objective often looks something like this, right? So you're trying to say you have a min-max game. You're doing max with respect to D, min with respect to G. And you're trying to do an objective like this, right? So your discriminator, you can see, is trying to like figure out which thing is data and which thing is generated, right? And your discriminator, your generator is trying to say, let me try and generate samples which maximally confuse the discriminator, right? So which make the discriminator mark it as real when it's actually fake. So this objective, you typically solve by like taking some steps on the discriminators, taking some steps on the generator, and back and forth, right? So if you like squint at this, it kind of looks like imitation learning, right? You're trying to say you have some demonstrations from your expert. You have your policy generating some trajectories. And this is kind of your generator, like you're acting in the world to generate the trajectories. And you want this thing and this thing to be indistinguishable, right? Like if you're really an expert, you would reproduce what the expert did, right? And so you can kind of think of this as a GAN where this thing is your generator and something that compares these two things is a discriminator, right? And so there's a class of methods called Gale, which try to like literally use a GAN to solve this, which say, try to solve a GAN where your discriminator step is trying to discriminate between trajectories that come from discriminators trying to discriminate between trajectories that come from sim and real, right? So it's trying to figure out is this like sim or not sim and real, between expert and non-expert, right? And your generator is trying to do RL with log discriminator as its reward, right? So it's trying to say that like your discriminator is trying to figure out which things were from your expert, which things from your non-expert. Your generator is trying to maximize the log likelihood of your discriminator. And at convergence, basically, it's going to be indistinguishable between the expert and the non-expert, or expert and your current policy. They become indistinguishable. But we'll try to work that out more formally. But that is kind of the intuition. Does that make sense? Sorry, one sec. All right, questions?
aspect is the probability that might be like one or zero, or like is it fake? Is the probability that it's fake or it's real?
D of X is, it's one if it's real. And zero if it's fake. Right, because you can kind of think of it as like your discriminator is trying to maximize the likelihood of real data and minimize the likelihood of fake data. Right, so which means that it's a binary classifier, which is trying to classify between real. Okay. So we're gonna try to derive how IRL is basically a GAN. It's not that obvious, but intuitively you can kind of think of it as GANs are trying to make the data distribution and the generator indistinguishable. IRL is trying to make the expert distribution and the policy distribution indistinguishable, right? And so it's kind of similar. One other thing to note is that often, if you can look at the discriminator, the generator objective, the generator objective only optimizes this guy. Like this thing doesn't depend on the generator, right? But this thing is often like hard to optimize. Like you have saturating gradients. And so the objective that you often optimize in GANs is a combination of this thing and expectation minus log D of G of C. And so you have some combination of 1 minus D of G and minus log D of G of Z, and they like show that it does a lot better. Right? So often the objective we're going to optimize is for the generator, some combination of this 1 minus D objective, right, which is the normal classification objective, and this minus log D objective. Okay, so that's a GAN. Yeah, we're fairly clear with what's going on with the GAN. Well, it's certainly more than one slide's worth of work, so please go read up. But this gives us a general idea. So how can we convert inverse RL into a GAN? And so the idea here is your generator is your policy, your discriminator is your reward, and you're trying to find a policy that makes it hard to tell which things came from the policy, which things came from the demo, right? And so the first paper that I just talked about is called Generative Adversarial Imitation Learning. It tries to solve an objective like this. Yeah. And so the objective for the discriminator is just classification. And you're just solving a classification problem. And the objective for the policy, which is your generator, is just to solve the second part, which is going to be an expectation of trajectories from your policy of minus log dt, right? Which is essentially going to be trying to maximize the reward of log dt. Yeah. You're trying to minimize expected minus log dt, which is saying you're going to try to maximize expectation of log dt, which is just doing RL. You can solve this with RL using log dt as your reward, right? And so you can derive Gale directly from the GAN objective. Just replace X with tau or T, right? And you're trying to say that your discriminator is trying to discriminate between, like the easy way to do it is have a buffer of real and fake, X them up, have labels of 0 and 1, have a classification objective, and then take log dt, use it as an RL objective. That's it. So that's what Gale does. It actually works surprisingly well, given this paper was in 2016. The problem with it is that it doesn't give you rewards, really. So if you think about this objective at convergence, what happens to a discriminator at convergence? Wait.
Oh, what is performance?
Yeah, so it's like completely confused, right?
Yeah.
And which means that the discriminator will always give you half. It's a binary classifier, so it'll always give you half, which means that it's like completely uninformative. So the challenge with this objective is that it doesn't give you a reward that is reusable. It'll give you a policy, but in inverse RL, we really want a reward that's reusable. Okay, so what we're instead going to do is make some simple tweaks to this objective to recover a reward function. The first thing we're going to notice is that when we have classification between two distributions, so let's say you're trying to solve a classification objective between two distributions. Something like this. This is what classification looks like. It's binary cross entropy. So if you do classification of this objective, you take the gradient of this thing with respect to B, you solve it and set it to 0. go through that exercise, but you'll get that the optimal discriminator is something like this. Right? And so it passes our sanity checks, right? Because if P and Q are the same, it'll be half. If they're not, it's not going to be half, right? And so the optimal discriminator you can show by just writing out the binary cross entropy objective, taking the gradient with respect to D, setting it to 0, comes out to P over P plus Q. We are going to choose a particular form of our discriminator that is going to give us a reward. And so we're going to choose our discriminator to be this. We're going to choose our discriminator to be 1 over z exponential reward of a trajectory divided by 1 over z exponential reward of a trajectory plus q. And q is going to be our like policy distribution. It's like a product of like policy likelihoods. Yeah. And so like intuitively you can kind of think of it as like it's like the same as a discriminator, but just like P is now 1 over the x bar, and Q is just product of policy likelihoods in a trajectory. And it seems like an arbitrary choice, but we will connect it and make it right. But when I say like we're going to choose our discriminator this way, that means we're just going to choose a slightly different architecture for our discriminator. So normally when you have a binary classifier, what you have is you have S or X or tau that goes in, and out comes a scalar. And then you take sigmoid on the scalar, right? So sigmoid is 1 over 1 plus e negative x, gives you a number between 0 and 1, right? And so it's a probability, right? So you feed in x or s or tau, it gives you some output. You feed the output through the sigmoid, it gives you a probability, and then you can use the probability in that log likelihood objective that I talked. What you're going to do here is you're going to do something slightly different. You're going to stick in tau into your discriminator. And then you're just gonna like add in a bias term for log z. So you're gonna output r, you're gonna add in log z, and then you're gonna q, and so you're gonna like subtract the log q term from here. And if you take the sigmoid of this thing, you take the sigmoid of r tau minus log z minus log q tau, you will like end up getting this thing, right? So like go through the exercise, but basically if you like use this form of the discriminator, the only difference is that you have like log q tau, so this is baked in, and like here you don't know anything, you're just learning all the parameters of your discriminator. Here you're putting some structure into your discriminator. You know log q tau, like it's kind of like a bias term that you added. And if you take sigmoid on this thing, your discriminator likelihood becomes this guy, right? So all you did is you changed your like architecture a little bit. And outcomes, basically your discriminator, you're still learning, you still don't know this guy. R is unknown, right? So the parameters of the discriminator are still the parameters of the reward function, but it's like parameterized a certain way. Okay, everyone kind of with me? So all we, right? So like, if you think of this as 1 plus x minus x, right? Now try and substitute in like, what do you call this? Substitute in x as r tau minus log z minus log q. And if you like substituted this as x, you will get this as your answer. So then, oh, you just have like 2 outputs. I mean, it doesn't really matter. You can just subsume both of these into the same thing. But basically, think of it as like you have a scalar output, right? So r tau is a scalar output, log z is a scalar output. You can either have 2 outputs or you can have 1 output, doesn't matter. But you can have 1 output, which is r tau minus log z. This thing is not coming, this is not a learned thing. This is coming from your policy. And you subtract those and then stick them into the sigmoid.
So the discriminator function approximately gives out 2 scalar outputs.
Yeah, so I guess what I'm saying is that it doesn't really matter because both of them are learned, so you can just combine them into one. So imagine that it just gave you one scalar output. Okay, so imagine it just gave you a scalar output that we consider r tau minus log z. Log z is just a scalar rescaling. It doesn't, or it's just a constant that you add. Right? So this thing is giving you r tau minus log z. You're gonna take this thing, you're gonna subtract log q, which is a known thing, not a learned thing, and then you're gonna pass this through the sigmoid. Right? And then that's going to give you this thing. So it's a good point that you don't need these two things separate. You can kind of like, they're just subsumed into the sigmoid.
The only fit two-digit case one is from your training data set and one is from your generator.
So this is just the structure of a discriminator. So it's when you do binary classification, you're going to take in an input and then you're going to output the probability that it belongs to class one. And the output that the probability it belongs to class 0 is 1 minus that, right? And so this is just telling me, I taken this input, this is giving me the likelihood that it belongs to class 1. And then you like feed this through like an objective, which is going to look like the binary cross entropy objective. Z is your partition function. If you remember, it is like this integral x bar theta dot. It's like the denominator of our log likelihood. So it's the same z that we had from earlier. My thing keeps dying. Yeah. Okay, so all we did is we made this small change where we just parameterize our discriminator this way, right? And then we're going to stick it into the same old GAN objective, and then we're going to show that it gives us that IO, right? So the only change that we made is we made a small architecture change in the discriminator where we stuck in log q, right? Before the sigmoid. Now, what we're going to try and do is we're going to try and stick this into a GAN. So the GAN objective looks something like that, right? And we're going to try and stick this into the GAN in place of D, and we're going to try and show that it gives us back inverse R. And we're going to try and stick in this particular form of D. Yeah. Okay, so we want to show that the generator optimization gives you max and RL, and the discriminator optimization gives you max and IRL. It's easier to show the generator, so I'm going to show that, and then we all should read the paper for the other one, so it's going to be a paper. But basically, let's take the generator objective. So if you remember the GAN, so remember all that we did is we said we're going to solve the GAN. We're just going to parameterize the discriminator in a particular way. And then we're going to take the same old GAN objective, this objective, and this objective for the generator, and we're going to optimize it with treating the discriminator parameters as your reward parameters and your generator parameters as your policy parameters. And we're going to show that it gives us max and IR. And so what we're going to do here is we're going to take this objective, which is the generator objective, right? If you remember the generator objective, it's trying to like confuse the discriminator, and then there's this term for optimization reasons. You stick in this definition of D into these guys, right? And what will come out is something that looks like this, right? So let's say Q is our policy, and so you sample trajectories from your policy. This term is 1 minus D. If you do 1 minus D, you're going to get Q over 1 over Z X R plus Q. That's the first term, right? And the second term is just D, so it's just going to be 1 over Z X R by the denominator, right? So all we did is we substituted this guy in here and here. Yeah. Now some things will cancel out, right? The denominators are the same, they cancel out. And what you get out is this objective, which is I skipped a step. So let's say you have min expectation of trajectory from Q, log Q minus log of 1 over Z X R, right? The denominators cancel out. And you simplify this a little further, you get trajectories from Q, log Q plus log Z minus R. Trying to minimize this with respect to Q, right? All I did is I just like substituted that in, denominators canceled, and I opened out the logs. That's it, right? Oh, shit, sorry. So this objective gives us essentially, you flip the min and the max, and you take a negative and you make it a max. And you get this objective, which starts to look a lot like max and RL, right? So log Z is a constant, doesn't matter. But this objective is maximizing reward plus entropy. Right, so log Q is our policy distribution, so log Q is our entropy, or minus log Q is our entropy. And so this is exactly max and RL. Right? So this means that our like generator is solving max and RL. And if you work through some more algebra, you can show that your discriminator is doing the same thing as your reward update. So the reward update being the same thing that we did in max and RL. This thing. So the important part here is that like intuitively, you can kind of think of the GAN as making these two distributions indistinguishable. Gale does that. It tries to make the policy and the data look the same. Doesn't give you a reward. But if you like choose a particular form of your discriminator, and you like do a GAN with that form of your discriminator, you can then start using that as your reward. And so there's this nice paper on the connections between IRL, GANs, and energy-based models that kind of like gets at some of the derivations that I see. Okay. Yes.
How do you get the L again? From the numerator to the line?
Here. Oh, sorry. How do I get this guy? On the left, on this term?
Yeah.
So if you look at B and you do 1 minus D, you get 1 minus 1 over Z x bar by 1 over Z x bar plus Q. Right? And you simplify this, so you simplify this by multiplying and dividing this one. And so there's this term.
What was the intuition for subtracting the log Q on the other slide?
Which slide?
The previous slide. Sorry.
The one with the GAN?
Sorry, this one, yeah. So.
Oh yeah, so the logic here was that basically if you like do your sigmoid, right? And you want your sigmoid to kind of like map out to this thing. Like if you speed, the thing that you feed into the sigmoid is r tau minus log Z minus log Q. And basically the log Q thing will disappear with, if you take x per log, you will get, if you take x per log, you will just get Q, right? And so that's how you get this thing. Okay. So, I thought this is just a cute connection, but basically you can show that in practice, often what you, like the easiest way to do adversarial IRL is just Gale, which is just just do this thing. Like look up Gale. All that Gale does is trains a classifier between expert data and non-expert data, uses log likelihood of the classifier as your reward, and it like works surprisingly well. So if you ever want to do adversarial IRL, that's the easiest way to start. So Shubham, when you're implementing baselines, just do that. Okay. So that's IRL. Does it kind of work? Yes, right? Otherwise they would have a field about it. And it also seems to work on robots. So this is some work from Alejandro. We kind of do walking around. So they call it adversarial motion priors. And so they had like lots of demonstrations of these dogs walking around. They use that to get a style reward. Like so it walks in particular styles. It like learns a reasonable style for walking, and they try to use that to guide navigation.
How do they get the demonstration?
I think they use mocap.
Like for an actual dog.
They might have done it either in simulation or did mocap for an actual dog. Yeah. Okay. So some takeaways on inverse RL. It gives you the potential for generalization. It gives you potential for generalization, potentially allows you to go beyond behavior cloning because your rewards are simpler than your policies. Because you're doing RL to re-optimize things, you don't have compounding error in the same way. And in certain scenarios, when it's hard to specify rewards, like by hand, it's easier to just demonstrate optimal behavior. Not always true, sometimes. The cons is that you have this nested optimization that's pain. And even if you fix it, you have these importance weighting issues that make it hard. It's inherently an ambiguous problem, right? Like if I pick something up, that doesn't tell me what the reward is. There's infinitely many rewards that can explain it. So you have to make some assumptions like this maxent type assumption. And there's some examples of scaling, but in general, maxent or just general IRL is hard to scale. And so in practice, what lots of people use is behavior cloning still, or things that look like behavior cloning. But one of you needs to fix this so we can all use IRL. And so
What is it that makes it hard to scale? Is it like a data problem?
because if you look at the adversarial IRL thing, you're like pushing up some stuff, you're pushing down some stuff. It looks like a GAN. And so it's hard to optimize things that look like a GAN.
So, well,
It's just like stability.
uh,
So like if you look at the training stability of something like a diffusion model, it's like a lot easier to train than a GAN. Because here you're trying to balance like in a GAN, you're trying to balance the discriminator and the generator. Here you're trying to balance the policy and the reward function. And so you take some steps on the policy, you take some steps on the reward, and you're trying to balance. And so it's like all the problems of GANs kind of like carry over. Okay. Yes.
So we know that GAN is like unstable during training. Why would we try to do IRL as a GAN?
Well, this was in 2018 or something when GANs were hot shit. I think there's a bunch of more papers recently that have been trying to cast IRL as a diffusion process, and they are still in their infancy, I'd say. Shubham isn't looking at some of them, but I think they're more promising. Yeah. But inherently, like the reason you might want to think of it as a GAN is it's like you have to push up your data and push down everything else. And a GAN does that by like having a generator generate what you have to push down. But like a diffusion model does it with noise. But either way, you have to push something down, otherwise you're screwed. Yeah? And so the thing that makes IRL hard is not the positives, those are easy, it's the negatives. Like how do you get good enough negatives to push down? Okay. Everyone happy with IRL? Questions, thoughts, concerns?
so what if like this, maybe this is a bad idea, but what if you learn a model dynamically from like your real data, and then you sort of start at states that are from your data set, and then you run like MPC or whatever, and you try to just optimize the reward using maxent.
You can do that.
And like, but there would be the problem of like the dynamics model isn't the same exact thing. Like, is there work that has looked into this? Like,
I think some of Matt Barnes's work, which the one that this Google is from, I think that basically does some version of that, like short horizon NPC rollouts. I don't know if they learn a model because they're using Google Maps.
yeah. Like the question that I really have is, you have a model that is like suboptimal or like not exactly the real thing. And so is there any paper or work that has like looked into like how much worse would you do, given that you don't have the true model, but you're using this procedure? Is there like
There's lots of work on RL, like forward RL, but I don't know what inverse RL. I think you might have to look that up. But I'm guessing that like essentially everything that goes wrong in your forward RL process will reflect in your inverse RL process. And so like you look up the MBPO paper, which talks about like if your model is wrong, how much error do you accumulate? Like that'll also reflect in inverse RL. So I expect all of the issues of forward RL to show up in inverse RL. Good. Cool. So let's, with our 20 minutes left, let's try to poke at multitask RL. Okay, so back in 2016, 2017, 2018, we did a lot of single task RL. So we would solve tasks like this, or single tasks like this, or like this with some of the techniques we talked about in this class, right? Model-based RL, model-free RL, imitation learning. But we really want to go to something that is more like this. So we want to say, I want to do, maybe these tasks are kind of tough, but tasks that look more like, or policies that look more like generalists that can solve 50 tasks or 100 tasks or 1,000 tasks. And so the question that multitask RL asks is, can a single policy solve 100 tasks, and what does it take to get there, right? And so, so far, what we've cared about is just like maximizing reward in a single setting. In multitask RL and meta RL, you care about distributions of problems. You don't care about a single problem, you care about a set of problems. And so the question that multitask and meta RL ask is, can we make these RL algorithms generalists, right? So we want a single agent that can either directly or quickly solve new tasks, right? So we want to say that a specialist agent is going to take in some observation of the world, try to generate behavior, try to generate actions, something that can, do a particular task. When you have a generalist policy, you want to have a single agent that still takes in observations, but takes in some specification of what you want to do. Could be a language instruction, that could be an image, that could be a demo, that could be cost parameters. It could be something comes out of inverse RL, you stick it into there. So it's something that specifies what the task you want to do is, and the same policy should be able to do all of the different behavior and generalize to new things, right? Whether that's zero shot or few shot. So the point of generalist RL is that we don't want to just think about special like training time performance. We want to think about test time performance. Okay, so the formalism that we need is we're going to define a distribution over MDPs. So if you remember MDPs, you have a state space, an action space, a transition dynamics, a reward function, an initial state distribution, and a discount. A distribution over MDPs is going to be a distribution over those things. Typically, you're going to keep the state and action space the same because you kind of want your agent to be able to act in all of them. But you're going to change your transition dynamics. You're going to change your reward function across all of these problems. And so you're going to have, rather than one MDP, you're going to have a distribution of MDPs, and you're going to be given some number of samples from this distribution. So one example is if you like go back to these tasks on the right, you're given these 50 tasks. They're drawn from some unknown distribution of MDPs. You want to generalize to new samples from that distribution. Okay, so so this seems fairly straightforward, right? We're just saying one MDP, single task. I have distribution of MDPs for multi-task. The other thing that you need for a distribution of MDPs is you need something to specify your task. So usually you'll have some like language or like demo or something that specifies what task you're trying to do. Otherwise, the agent doesn't. So what makes this hard to do? Like, what's kind of weird about this formalism? Rewards are different, but then you have like behavior being different because your policies are being conditioned on task specification, right? So you're conditioning on task specification, which means you know which of the rewards you're trying to optimize. I think the thing that I find a little hard, well,
So basically what we're doing here is we're having a bunch of different policies.
yeah, I guess it's not that different if you have a bunch of different policies or a conditional policy. Having a conditional policy is something like a single policy which takes in your task description. The difference if you have a discrete set of policies, it's not clear how to generalize to the next one.
Yeah.
Whereas with a conditional policy, you can generalize to the next one if your function approximator generalizes.
Right, but we're still taking in like a task descriptor here, right? So we're still essentially having a policy per task.
Kind of.
We're not.
I guess you're sharing parameters, right? So like the way you have some neural net that'll take in an observation and some task descriptor, and like you can share information between different tasks, right? So it's not like completely separated. Like completely separated would be like 8 different models, and then each of them just take an observation, but they're like completely separate. But you could like, if you have a parametric model that takes in a task descriptor, you could share. That's the premise. I think the part that I find a little hard to wrap my head around here is the distribution over MVPs. Like, it's easier to think about a distribution over initial states, but if I have like 10 different tasks, right? Like, how do I know that these tasks, like if I give you another task, how do I know if it's in the same distribution? So these characterize a distribution implicitly, but if I'm given task n+1, or like a distribution of tasks n plus one, it's hard for me to know if they're the same distribution or not. So I think an interesting question that I don't think we really know the answer to is how do you characterize distributions of problems and how do you compare tasks to each other? Like the metric is not very clear. And so I'm going to use this formalism, but it's know that I don't fully understand. I don't think anyone really does. And so that's an interesting question. Yeah.
Or how's this different from, or like, why is that as much of a concern when you have the new task? Would you just use the existing model as a like warm trained model and then retrain with new task? Like, how's that different from?
You could do that, but I guess it's not like a proper metric between two problems, right? Like you could have two things where the policy initially does pretty badly, but you only need to make a few changes in the policy. Like imagine you're going left versus going right. Right? If I start going left, I'm going to do pretty badly for going right. But if I just like flip the actions, then I like have an optimal policy. And so it's not super obvious to me how to like characterize the difference between tasks. Because like in some ways what you're like trying to characterize is how many bits of information do you need to flip in order to go from one task to the other. And I don't really have a good formula. Okay. Yeah, go ahead.
In case if here to that's auto distribution, so you cannot have a shared
Not have a shared with it.
shared neural network with it.
You can. It might not do very well.
I don't-
But since we don't even know how to characterize something as out of distribution or not, then it's a little budget.
I was trying to ask, like, presumably, I guess, like, if your action space is the same and you like scale your model, I guess presumably, like, any problem with the same set of like actions, you could learn a generalized policy for it.
If you can cover all the problems, right? So usually machine learning problems are like focused on particular data distributions and they're good on those data distributions, not on others.
Yeah, yeah.
And so like here you have to choose, you can't be like a master of all. So you're like picking a certain set of distributions, right?
Yeah.
Which are like natural tasks and say you're going to be good on natural tasks. But it like no free lunch will hit us if we do all problems.
Yeah.
Okay, anyways, that's just my existential doubt. Yeah, go ahead.
And the probability or like the distribution and
Yeah.
the likelihood and then MTP basically like is like, I don't know, I'm just thinking like, how do you choose what distribution is that just
I think different problem statements have it differently. Right? Some people like in simple examples, you just choose it. In certain cases, you like will choose your tasks based on like what data people collect. So you like let people collect data, and some people collect lots of picking, and some people collect some other stuff. And so like there's a natural distribution of what people prefer, and so that defines your task distribution. You could have like someone who is your like let's say you're deploying this in a factory, like your factory requirements could define your task distribution. Like I really care about picking and much less about sliding. So I think your problem defines your task distribution or your data collectors define your task distribution.
Here we have like the same states and actions, so is it also possible to like do meta learning with robots, so like having different robots, different action spaces?
Yeah, it is. It's harder. But I think especially if you make the state space images, like often the solution when people like you're talking about cross embodiment learning, right? So like you learn across robot. Like they'll often take like images in and then they'll have like different heads going out for different dimension robots or whatever. So they have like a multi-headed approach. Yeah, but it's like a super popular area of research. Right?
And just a follow-up question to this. If you have two different robots, how do you get intuition that they are sharing the same thing?
I don't know. I think there's like some things that are obvious, like if you have similar degrees of freedom, similar morphology, like from an eyeballing perspective. But I don't know if we have like a very good metric to characterize how similar morphologies are. So do you have a question? All right, so let's keep going. So what we're going to try and figure out is how to define and solve this multitask or meta MDP problem. we're going to try and learn a policy which takes in an observation, task specification, produces a behavior, produces an action. Why would we want to do this? The hope is that you can learn faster by sharing some data. Right? So, like we were just talking about, you want to learn faster by like sharing data between different tasks. So rather than having completely separate tasks, you want to have one model that can take an observation task and like share data between the different tasks. Right? If you're just going to have no data sharing, you might as well just learn separate policies. And then the second hope is that we want to generalize quickly or immediately to new and unseen tasks. So like we've seen in vision and language, like the paradigm of pre-training plus quick fine-tuning or zero-shot generalization has worked really well. And so the hope is, can we do that for robotics, or can we do that for RL? Okay, so that's why we want to do it. Now let's think about how to do it. How are we doing that? So the formalism we're going to kind of assume is that there's going to be some parameter, there's going to be some vector omega I that's going to characterize our task. That could be a task ID, so like a one-hot vector which is telling you which task you're in. It could be a goal image. It could be a video telling you what you're trying to do. It could be a language instruction. It could be something characterizing your objective in a way. And so now you're going to say your distribution is over that omega I, and that omega I defines your transition dynamics and your rho. And you're going to try and reformulate your problem to say that your state space is now going to be not just your state space, but state space and omega I. And your policy is now, or your transition dynamics and your reward are also going to take in omega I. And so basically this omega I lets your transition dynamics change or your reward change. And your policy that you're going to try and get is also something that takes in S and omega I, right? So you're trying to learn like phi, A, of S and omega I. So when you hear like language condition policies and so on, you're just like taking your state, also feed in language, also feed in a goal image, also feed in instruction. And so the first and simplest thing we're going to do is we're going to formulate this multitask MVP, saying that you know omega I, you're going to define a distribution over tasks. And you're going to feed in omega I as part of your state and try to use plain old RL to learn a policy. But because it's trained over multiple different tasks, it should generalize to new tasks from P of omega I. Okay? So the only difference is you've expanded your state space. So it's the same problem, you just expanded your state space. Your state space has a special part, which is omega I, which doesn't change across time. Right? But it defines your transition dynamics and it defines your reward. Okay, so that's the first and simplest thing we're going to do. So we're going to try and do soft actor critic or whatever our favorite actor critic algorithm is. We're just going to try and feed in omega I as part of the input into our actor and actor. And so your objective is going to be, let's maximize the expected sum of rewards over omega sampled from P omega and trajectory sampled from your policy. Right? So if you remember, RL was just this. Maxent RL just puts an expectation on your probability distribution of your tasks, right? And so like Claire was just saying, it's basically given to us by some problem definer. We're just going to try and maximize this expected sum of rewards by feeding in omega as part of your policy or your Q function. So if you do that, you get an objective that looks like this. You sample data from a bunch of different tasks. You collect all the data into a buffer, but you just add in omega I into your buffer along with your states and actions. You perform actor and critic updates same as usual, just going to add in omega I. So the only difference, I guess I've used like 3 different notations here, but tau is omega, or yeah, tau is omega. So basically it's saying that like learn a multitask Q function, learn a multitask policy. You're just conditioning everything on the like task descriptor. Okay, and if you do this, you start seeing pretty terrible performance. And so this is single task RL. So this is what happens if you run RL on one task at a time. And this is what happens if you run multitask RL. Which is supposed to be better. It's supposed to be taking us to the promised land, and it is at 18% or something. Yeah, not good. Right? And so if we naively run multitask RL, which means that you just feed in QSA omega I and pi SA or pi A given S and omega I, you get really terrible performance. Whereas single task RL works, so you know that it's not that RL doesn't work. It's more that something about the multitask problem makes it hard to optimize. And for the rest of this, I'll see you guys on Monday. Thanks. We have to come on Monday, otherwise we'll never know. This is on those multitask meta world environment. Those like the 50 environments that we had earlier, like these ones.
Using a bigger network to solve the
No.
problem.
Not in this setting.
Because in another